Welcome to the next video on PRMS training. We're going to talk about the potential ET process. You can see quite a few different options, different module options. You can set these in the control file just like the other ones. Climate by HRU is also an option here, but I don't go into that. So I'm just going to go through these, talk about the equations. And most interesting on these is what kind of input data is required. In this case, we're looking at the Jensen-Hayes module, POTT_JH, and you can see the equation here. And if I click, these yellow things are highlighting parameters that you have to set for each HRU. These are variables. This green variable is coming from this shortwave radiation distribution module, either DD or CC SOLRAD. So that's coming from somewhere else. And these red ones, these are inputs. So you've got to specify temperature. This module is a temperature-based estimate of PET. Going on to Heyman. This is the second option you can choose, second module. There's one parameter, the Heyman coefficient. SolTab sun hours, that comes from the solar radiation module. In this case, we're using average temperature 3 times in the same equation to come up with this humidity term. So again, this is the Heyman equation here. The Heyman method is another temperature based. Basically, all you have to do is input temperature. This is the third module that we have in PRMS, the Hargrave-Samami formulation. You can see the equation here. In this case, you have to input this HS-KRS. That's a parameter, HRU by month. Again, shortwave radiation is coming from the SOLRAD module. We're using maximum, minimum, and average temperature, all 3 of those temperatures in the same equation. So another temperature-based equation. The fourth module that's available for the potential ET process is the Priestley-Taylor. There's a bunch of equations computing the different terms. The fundamental equation is down here, 1-60. And you can see there are 2 parameters you need to provide: the elevation and this Priestley-Taylor alpha. Latent heat of vaporization, I had the equation for computing that in the previous one. Again, solar radiation, and then we're computing this saturation vapor pressure slope, and that depends on temperature, and temperature in here for this heat flux to the ground. Then the final one is the Penman-Monteith formulation. The final equation is going to depend on dew point, so you actually have to input the humidity per HRU. You have to input the temperature, come up with the actual vapor pressure. We need the saturated vapor pressure. That can be computed from the temperature on the HRUs. Subtract those 2 and you get the deficit, which is what the equation is going to use. Penman-Monteith also needs net long-wave radiation, and this is the equation we're using here. We've got these green terms here. Highlighted green terms are coming from these other equations. Again, it's using temperature. And then we finally get to the big equation that computes the potential ET. This is the form of Penman-Monteith that we use. All these green terms are variables computed elsewhere. You see we've got 3 parameters in this case: Penman-Monteith D, Penman-Monteith N, and a D again. So there's really just 2. And this also requires wind speed as an input. In this particular Penman-Monteith formulation, you need to input the humidity, you need the temperature, you need the wind speed, and these 2 parameters. And then the final option is if you have pan data, very simple equation here. You've got the actual evaporation from the pan that has to be input in the data file, and then this is a parameter, and from that you'll get the potential ET. I put this in here. Sometimes people want to know what we're actually doing with the potential ET, and what we're doing with it is we're computing actual ET. And so depending on the soil type, you get a ratio of the actual to potential evapotranspiration and the ratio of the antecedent soil moisture to the total soil moisture. And depending on the soil type, you can come in with the water availability and you'll get the ratio of actual to potential ET. That's what this is used for. One thing that's kind of good to know is available is this atlas of potential ET values. This comes from the National Weather Service, or NOAA, developed by Farnsworth. It's been a few years now, but these are still pretty useful climatological monthly means for potential ET. And I just put this in here. This is kind of a personal issue. We've had a lot of questions about PRMS related to using these temperature index methods. The problem, or I don't know if it's the problem, but the issue is that as temperature increases, so does potential ET, because potential ET is a function of temperature, of only temperature, in all but the Penman-Monteith method. There has been many papers published where people have actually observed that reference ET or potential ET has decreased despite temperatures increasing, and that's despite actual ET increasing. If you think about the terms of the equations, humidity, solar radiation, wind speed, as well as temperature, right? Those are all terms in the equation. So even though temperature is increasing, some of these other things could be decreasing the temperature. Our rebuttal is that you could use the Penman-Monteith module. If you have all that data, go ahead and do it. But we would also say, does it really matter that much if your application is in a soil moisture limited basin? Something to think about. And that concludes my presentation.